Hello, Honors Chemistry. It's April 1st. It's good to see you. Can't see you. April Fools. We're going to look at page 510 today. At the very bottom, total enthalpy change. And you can see the formula down there. Let me show you how it works. You saw on page 511 that we did the problem in the last lesson, but we can check our work. And if you take a look at the bottom of page 511, you see the beginning of that formula again. And on the next page, you'll see how they checked their work. They didn't go through the long, complicated thing that I went through on page 511 to show Hess's law, but rather they just used that formula. If the equation has in it substances that can be found on that table of formation, and that would be R66, table B14, then we can use this equation because it's built around enthalpies of formation. So let's just do practice problem number 1, page 512. Calculate the enthalpy of reaction for the combustion of methane gas to form carbon dioxide and water vapor, and that would be liquid because in standard conditions, water is a liquid. So let's just start with Ch4 combustion. We're going to call water a liquid. This is gas. It forms water vapor, as you know, but as soon as the vapor is formed, its environment is so cool compared to that hot vapor from burning the methane that it condenses on the vessel that it's in. And then this is a gas, and that's a gas. 1 carbon, 1 carbon, 4 hydrogens, 2 hydrogens. We got 2 oxygens, we got 2, and 2 make 4, so we got 4 oxygens. That's the first step, is a balanced equation. It always is. And if you want the delta H, that's what it wants, enthalpy of reaction at standard conditions, you're going to go like this. It's always going to be products minus reactants. So delta H, we learned, was the enthalpy of the products minus the enthalpy of the reactants. You learned that at the beginning of the chapter, of this section, I mean. All right, so we're going to go with the number of moles of carbon dioxide is 1 on the balanced equation. And you're going to take that times the enthalpy of formation for carbon dioxide on page R66. Carbon dioxide is negative 393.5. And then you're going to add to it 2 moles of water as a liquid. And water on this table on page R66 is called hydrogen oxide. And we're going to go for the liquid kind, negative 285.8. And then we're going to go ahead and we're going to subtract, according to that equation there, 1 mole. And then methane, I think they gave it to us in, well, no, it must be on this table. Methane is negative 74.9. And then you add to that 2 moles. And the enthalpy of formation for a element, like oxygen is, it's not a compound, is 0. And so we're going to have to do that. And so we got negative 393.5 and negative 2 times that. So we're just going to go 393.5 plus 2 times 285.8 equals, and then turn it into a negative. And then a minus a negative is an add. So we'll add 74.9 And we're going to get negative 890.2. And the answer is negative 890.2. kilojoules. That's the heat of reaction for that equation. All right, let's go on over to sample problem C on page 513. Now I'm going to show you how to do the enthalpy of formation of pentane. And I'm going to ask you to do one of these. By the way, this formula right here that I just used is used all the time in college chemistry. And so you can do multiple problems with just that formula right there. If they are listed, if these substances are listed, they're in the equation on that table back there. There's, of course, extended tables in bigger volumes. So we want the formation of pentane for C5H12. Of course, we're going to form that. That means we take the constituent elements of C5H12. That would be carbon and hydrogen. Carbon's a solid, hydrogen's a gas at room temperature at standard states, and this is a gas. Okay, and 5 carbons, 1 carbon. 12 hydrogens, 2 hydrogens. That looks like the balanced chemical equation, and we call that our target equation. Remember doing this on yesterday's lesson? And so what we'll do here is that's not listed in the table back there. You can go look for pentane back there on R66, you won't find it. So what we're gonna have to do is find a circuitous route to get to that target equation. So what I'm gonna do is I'm gonna burn carbon, graphite, to form carbon dioxide. And then I'm going to burn hydrogen, form liquid water. Okay. Now, you could say that this is formation of carbon dioxide and look for the enthalpy of formation. Or you can say it is combustion and look at the enthalpy of combustion. For carbon dioxide, in this case, combusting of carbon. So let's just take a look at that in the back of the book here. R66 formation, we're talking about carbon dioxide. Here we go, negative 393.5. Okay, and then the heat of combustion for carbon is on page R60, and that's table B5. You look at carbon, which is graphite, soft carbon, negative 393.5. Do those two enthalpies represent this equation? Is this formation or is this combustion? Either way, it's the same thing. I'll just call it formation, just for funsies. Okay, and then this one here is formation or it's combustion of hydrogen. It's exactly the same deal. I'm going to look at the formation of water, liquid water, and I'm going to find that it is hydrogen oxide, same thing, negative 285.8. Kilojoules per mole. Kilojoules per 1 mole. Kilojoules per 1 mole. Okay, now I'm going to have a third equation because I got carbon taken care of in here. I've got hydrogen taken care of in here, but I don't have that thing. So we're going to go ahead and say, we're going to burn that. C5, these are tools that are in your toolbox, you might say. Now, what do you get when you burn a hydrocarbon? Do you get carbon dioxide and water vapor? Okay, in this case, it's going to liquefy as soon as it's made, and then this is a gas. That's a gas, and that's a gas. All right, what's delta heat of combustion for this pentane? Well, let's go over there. Pentane is on page R60. R60. Pentane is negative 3535.6. kilojoules per 1 mole. Okay. Now, is pentane on the correct side of the equation? If we want it to be on this side of the equation to make it like the target equation, we better flip that whole thing. So let's flip it and put carbon dioxide over here. And I'm not even going to write the state of matter because I don't want to complicate things right now. Got that? Okay, now let's balance it. 1 carbon, 1 carbon, 2 oxygens, 2 oxygens. That looks good. 2 hydrogens, 2 hydrogens, 2 oxygens, 1 oxygen. That's balanced. And when I flip this thing, what do I do to that sign? I make it positive. Negative to positive. All right, then what do? I cross this thing off because I don't want to get confused. I flipped it, changed the sign. Now we're going to go ahead and balance this. 1 carbon, 5 carbons. 2 hydrogens, 12 hydrogens. With the oxygens last, we got 10, and 6 makes 16. We got 2 over here, so we need an 8. All right, now, we're going to want to go ahead and take these heats of formation. Before we do that, let's start crossing off some stuff. I'm going to use red. I have carbon dioxide over here and 5 carbon dioxides over there. So I'm going to have to multiply all of this times 5. And when I do that, I'm going to get a 5 right here, a 5 right there, and a 5 right there. Now I've got 5 carbon dioxides that I can cancel out by subtracting them from both sides. Now I got 6 waters over here and only 2 over there. So I'm going to have to multiply this whole thing by 3. And when I do that, that 2 becomes a 6. A 3 goes right there, and a 6 goes right there. Just go ahead, and I can take 6 waters out of the picture. Let's see. We want 5 carbons. Oh, we got oxygens to cross off. We got 5 oxygen molecules and 3 more moles of oxygen molecules, and 3 more makes 8. And we got 8 oxygens over here. We good? Now we've got ourselves the equation of interest. We've got 5 carbons. But before I do that, let me just tell you this. If I'm forming 5 moles of carbon dioxide, I need to multiply that thing times 5. And if I'm forming 6 moles of water, I need to multiply that times 6. Because don't forget that listing on the tables for 1 mole. And then that'll be good. And this remains just like it is because there's a big fat 1 right there. Now, do I have 5 carbons? Do I have 6 hydrogens? Do I have methane? And everything else is crossed off. So now let's see if we got the right answer. Now let me tell you what the right answer is. Well, no, I'm not going to flip the page. I'm going to calculate it first. And you're going to flip the page with me. Negative 393.5. Let's see, that's negative, and that's positive. Let's start here. 3535.6, this dime store calculator. Minus 6 times 285.8. Minus 5 times 393.5. It says it's negative 146.7. It says that delta H formation of 1 mole of pentane is negative 146.7 kilojoules per mole. Negative 146.7. Let's turn the page. Boom, negative 146.7. Worked out good. Now, how many more of those are you going to have to do before you feel comfortable? A bunch. Try doing the homework best you can. Give your best effort. Thank you for watching. See ya.